Okay, we're going to do the next experiment, which is kinetics, introduction to kinetics, and we'll be doing the method of initial rates. I'll explain what that means in just a moment. We're going to be doing it with a simulation that you use online, but the data you get from it is very similar to what you would get if you were in the lab actually doing the experiment. So let's talk about kinetics first, because a lot of times people learn about kinetics in general chemistry too, but they never learn why you do kinetics. Well, why do we do kinetics? We don't do it just to torture students. Sometimes they think that. But no, we do kinetics to try to get an elucidation of the mechanism of the reaction. What is the mechanism of the reaction? Well, the exponents, what we call the order with respect to the different chemicals that are in the reactants that go to products. The order with respect to them does not come necessarily, well, it doesn't come at all from the coefficients from the balanced chemical equation. It really comes from the coefficients from the balanced rate limiting step. What is a rate limiting step? What does that mean? Well, let's say I have a reaction that's simple. A plus B goes to C. And you think, okay, well, it's a simple chemical reaction. A hits B somehow and they react and there's a bond that forms and it makes another compound called C. Well, maybe, but maybe not. What if what really happens is a two-step mechanism? First, A has to react with another A to form 2A. And then this 2A is capable of reacting with B to go give us C plus A. A gets kicked off again. Well, look, if I combine these two reactions, I can cross out those A's on that side and the two A's on that side. And overall, I have A plus B just give me C. But the actual mechanism is this two steps. And what if this was a very slow step and this one very fast? Well, obviously, the rate of the reaction is dependent upon the slowest step. Therefore, the order with respect to the different chemicals comes from the rate limiting step. In this case, because it was 2A, we would end up with A squared. The order with respect to A would be 2. The order with respect to B would be 1. So from that, we would say, oh, well, the rate limiting step must be, well, actually, I think the order with respect to B would be 0 because it's not it is involved in the rate limiting step, so it would be 1, sorry. So in this case, we would say, oh, well, it must involve some previous reaction that makes 2A, and then 2A reacts with B to give us C because that's what the order of the rates from the kinetics tells us. So that's why we do kinetics. So what kind of kinetics are there? Well, there's actually two different forms. We're going to do the method of initial rates, and then next week, I think you're going to do an actual experiment in your home that involves the other method, which is the method of pseudo rates, which really is rates, but it's a different form. We'll talk about that next week. Method of initial rates. Well, like it sounds, we're getting the mechanism of reaction initially before the concentration of the different reactants change. What does that mean? Well, let's look at an experiment. And we'll look at the first experiment we're going to look at in the handout, and we'll talk about what that means. So if I have something like this, well, what I want to do is I want to set up my concentrations of my reactants, and then I want to measure the rate of the reaction before the concentration of my reactants changes significantly. Why? Well, if it's second order in B, when the concentration of B goes to 1/2, the rate of the reaction goes to 1/4. It slows way, way down. I want to get the method of initial rates before there's any change in concentration. And because there's no change in concentration, no significant change, I can change the concentration between trials, and I can say, how does that change in concentration affect the rate of the reaction? Based on how that happens, I can determine what the order is with respect to that chemical, right? So let's look at this example. So my rate of my reaction is going to be equal to K. That's the constant for kinetics, and that's dependent upon temperature and a whole bunch of other stuff, but not concentration, times A raised to some value of A from the rate limiting step, and B to some value B from the rate limiting step. So let's say I do two reactions. The rate of the reaction 1, concentration of A1, concentration of B1. I do a second one, rate 2. K is the same. A raised to the A is 2. B raised to the B. Well, let's say I kept the concentration of B constant. Then the concentration of B is the same in both of these. K is the same of both of these. Concentration of A is different, and the reaction rate is different. Well, if I divide these, I can see that the K's cancel out, the B's cancel out, and I'm left with rate 1 over rate 2 must be equal to the concentration of A raised to A over A raised to A, and that's A1 over A2. Okay, well, we know when I have something that is raised to the power like that, I can say rate 1 over rate 2 is equal to the concentration of A1 over the concentration of A2, the whole thing raised to A, because essentially it's the same thing. I want to know what A is, so what can I do? Well, I'll take the log of both sides. In this case, I'll use log base 10. So I take log base 10 of rate 1 over rate 2, and that's going to be equal, when I put the log with an exponent, that's the same thing as the exponent times the log of. So that's going to be equal to A times log base 10 of the concentration of A1 over the concentration of A2. Well, I know what rate 1 and rate 2 is. I know what A1 and A2 is. I can solve for A. A is going to be equal to log base 10 of rate 1 over rate 2 divided by log base 10 of concentration of A1 over concentration of A2. Okay, that's how I solve for A. Pretty easy. So then what do I have to do? So this is the way you approach these problems. You find two trials in which the concentration of one of the components changes, the concentration of the other one does not. The one that changes is the one that you're finding the order with respect to. So let's look at it. Let's do it for A in this case. So what two trials does the concentration of A change, but the concentration of B does not? Trials 1 and 2. Concentration of A went from 0.1 to 0.15. Concentration of B stays the same. So then, using our little formula here, A must be equal to log, and I always do fast over slow. You have to keep the concentrations with the rates. Okay, concentrations with the rates. So if I'm going fast over slow, my fastest is the 6.14. So that's log of 6.14 over top of my slow 2.73. And that's got to be divided by log of, and got to keep the concentrations. That's 0.150, 0.150 over 0.100. And if I calculate that out, and you should do that in your calculator, I'm going to end up with A equal to 2.00. Now, it doesn't always work out to an exact number like that. Sometimes it'll be 1.98 or it'll be 1.79 or something like that. For this experiment that you're going to do using the simulation, don't round it up to the nearest whole number. Just write down whatever you got with the digit and then to the tenths hundredths place. And that's how it'll be graded based on the values you got for the tenths hundredths. I'll take your data, put it in my spreadsheet, and it'll calculate out the rate for the rate order with respect to for it, and that's how you'll be graded for it. The trial works really, the simulation works really well, and I'll talk about that when we get done with this. So there is a trick. There's a trick you can do, and I'll show it to you. The trick can't be used for this lab because it won't work, but it can be used on exams and quizzes if you have something like that. And that is, okay, if I have something raised to the first order, B to the first, that tells me that if the concentration of B doubles, well, 2 raised to 1 is what? 2. So that means if this equals X, then the concentration of 2B must be equal to 2X. That is, if it's first order, when the concentration doubles, the rate doubles. If the concentration doubles, the rate goes up by 8. What must it be? Must be cubed, right? Because 2 cubed gives me 8. If the concentration doubles and the rate goes up by 4, what must it be? Must be second order, because 2 squared equals 4. So if the concentration doubles and the rate doesn't change, what does that tell me? Must be 0th order, because 2 raised to 0 is 1. 4 raised to 0 is 1. 395 raised to 0 is 1. So even if this concentration doubles, the rate stays the same, it must be 0th order. Now, does 0th order mean that the compound's not involved in the reaction at all? No. It only means that the compound is not involved in the rate limiting step. It still appears in the overall balanced chemical equation because it's part of the reaction. It's just not involved in the rate limiting step. That's why we do kinetics. So how can we use that for this one? Well, I look at B and I look at trials 1 and 3. The concentration of B doubled. The rate essentially didn't change. That tells me what? I already know. B must be 0th order. Therefore, my overall reaction rate for this, the rate is going to be K times, what did I say? A raised to the second, B raised to the 0. And often when you do that, you just don't include the B in there, and you say the rate is equal to K times A squared. Tells us that there must be a reaction that has A plus A goes to 2A, and that's the rate limiting step that happens during the reaction. Okay? Does that make sense? Let's do another one. This one, we can solve it by using the shortcut method. Again, I remind you, you will not be able to use the shortcut method on the lab. It doesn't work out that way. None of them are this simple, okay? So don't plan on doing that. But let's see if we can figure this out. So we look for 2 runs in which the concentration of one changes, the other does not. Well, we look, trials 1 and 2, B doubled, A didn't. What happened to the rate of the reaction? The reaction rate doubled when the concentration of B doubled. Therefore, what does that tell me about B? B must be first order. Rate doubled, concentration doubled, must be first order. Then for A, I look at trials 1 and 3. Well, can't do that because B changed when A changed. That's no good. But I look at trials 2 and 3, and I say, the concentration of B stayed the same. Concentration of A doubled. What happened to the rate of the reaction? It didn't change. Therefore, A must be 0th order. So I've figured out the order with respect to the reaction. Now, another thing we can do here, too, is we can figure out what K is. How can we do that? Well, we've got the rates and we've got the orders. And technically, you should be able to pick any of them, and they're going to be close, but you just pick one. So the rate, say, 2.5 times 10 to the negative 2 molarity per second is equal to K times, we don't have to worry about A because it doesn't affect anything. So we end up with B, and what is B? B to the 1. Well, let's say B is 2 molar. Therefore, K, and it's lowercase k, not uppercase K, must be equal to 2.5 times 10 to the minus 2 molarity per second over 2.00 molar, and therefore molarity cancels out, and we end up with 1.25 times 10 to the negative 2 seconds minus 1, or 1 over seconds. The units that are attached with K changes for all different experiments. There's all kinds of crazy numbers of them. You can't do it really easily. All right. You guys go ahead and do it for these. Just pause the video, work them out, and then we'll go through and show you what we got. But first, you try and do it. Okay? All right. So, again, what we want to do is we want to find out we've got rate equals K times A to the A, B to the B, C to the C. What are we going to do? Well, we need to find 2 reactions in which the concentration of one of the reagents changes and the other compounds do not change concentration. Well, let's look at trials 1 and 3. 1 and 3. A stays the same, B stays the same, C changes. Okay? So, sort of a shortcut once you do enough of these. You can set up the equation, but it's going to end up being C is going to be equal to log of rate fast, which is the fastest of these two, 1.102, over top of rate slow, that would be number 1, right? 0.480, divided by log of, and the log can be ln, log base 10 or log base e. It doesn't make any difference. You just got to make sure you keep the concentration with the rate. Since I use this rate first, and we're doing C, I have to use this concentration on top down here, 525 divided by my 0.398. And if I did that correctly, what should you get? You should end up getting a value of C equals 3. Is that what you got? If not, go through it. And again, you may get a value that's slightly different, but these are usually designed to give you whole numbers. That's not necessarily true in real life, not necessarily true in the experiments you're going to do. So what's another one we want to do? Well, we've got C. What else do we want to do? Well, let's see. We can do B. So if we look at B, we want to find one where the concentration of B changes, but A and C do not. So B changes between 1 and 2, but so does A, so that's no good. B changes between 1 and 4. A stays the same. C stays the same, so that's what we're going to use, 1 and 4. So B is going to be equal to log, I'll use base 10 here, fast over slow. The fastest is this one, 0.563 over top of the slow one, which is 0.480. And that's going to be divided by log base 10 of the 0.250. That's the concentration that went with my fast, over top of 0.213. That's the concentration that went with slow. And if I put that in and I calculate it all up, I end up with 1.00, I think 4 or something like that, essentially 1. All right, so now how about the last one? Well, again, to be able to get A, I have to find two reactions in which the concentration of A changed, but the concentration of B and C did not. So what do I got? Well, A changes in 1 and 2, but so does B. No good. A does not change between 1 and 3. A does not change between 1 and 4. A does change between 1 and 5. B does not change between 1 and 5. C does not change between 1 and 5. Bingo, I got it. So now it's going to be log of fast over slow, and I'm using 1 and 5. So log of fast is 1.376 over top of 0.480, and that's divided by log of my 0.251 over top of my 0.151, and that's going to give me a value when I do my calculations. Comes out to be 2.07, which would be essentially 2.00. All right, so that's the way you do those calculations. And I showed you how to do the K calculations to find out what that value is. No problem. They're not difficult, but again, you can do the shortcut only if it is absolutely crystal clear that the concentration changes by an amount and the rate changes by an amount that can be easily squared, cubed, 1, or 0. If it's not crystal clear, you've got to use this method, otherwise you will get the wrong answer, and it happens all the time. So for this experiment, what are you going to do? Well, we're going to look at the rate of reaction, the order with respect to two reactants. One is A, the other one they list as BC. So what we're going to do is we're going to put in a starting number of molecules of each. One is going to be like an order of magnitude greater than the other. That way, there won't be a significant change in the number of the other molecules. Then what you're going to do is you're going to time the reaction, and you have to use their stopwatch to do it. The reason for that is I did the experiment, and for like the order with respect to A, in the 10, one that I put 10 molecules in, I got values from 300 seconds to 3,000 seconds. Well, 3,000 seconds is almost an hour. There's no way. That reaction, when I was doing it, took like maybe a minute, a little over a minute. So it's obviously not truly measuring seconds, it's measuring milliseconds of some sort. But it has units a second. Use their units, use what they say, use their stopwatch. You have to set the stopwatch up to work correctly, but that's okay. Play with it and run it a couple of times to make sure you get used to it. You have to reset the stopwatch after each run, and then you click begin. You wait till 5 of the products show up, stop it, look at the time. Reset the stopwatch, begin the experiment, wait till 5 of the products show up, stop it, reset the stopwatch. Each time you begin it, it'll reset the experiment. It just won't reset the stopwatch. I don't know why. It's very annoying. Do that for 10 trials, then take the average. Like I said, you're going to get a huge variation I got between 300 seconds and 3,000 for the first one. And then all of them are faster after that. So it takes a little bit of doing, but I did the entire experiment in maybe 20 minutes. So you shouldn't have any problem getting it done in no time. And then do your calculations using your logs, a fast over slow. And instead of concentration, you're going to use number of molecules. One experiment, it's going to be 10. The other experiment, it's going to be 20. No problem. Should be very easy calculations. Make sure you read through the introduction to the experiment, and make sure you read through the handout that goes along with this, so you understand what I'm doing when I'm working these problems. If you have any problems, any misunderstandings, I don't know what the heck's going on, email me and ask me. We can set up a Zoom and do it. If you have any questions anytime about what's going on in lecture and you want a little bit of help, email me. Set up a Zoom. We'll go through it. I teach the lecture enough. I should know what's going on. If I don't know what the heck you're talking about, I'll make it up. No, I won't. I'll tell you I don't know, but I can't believe that would happen. And I'll try and help you with whatever it is you're doing in the class. Other than that, stay safe. Make sure you do this and make sure you understand what's going on. And I will see you next week.